Hi everyone, today's topic is energy in thermal process. In this topic, we start with the basic states of matter. Either you say states of matter or you say basic phases of matter. Okay, we know there are three basic states of matter, that is solid state, liquid state and gaseous state. Of course, there is one more phase, that is the plasma state, which we are not discussing in this video. Okay, so our second topic is phase change, or you can say state change or change of state. A phase change is a physical process in which a substance transitions from one state of matter to another state of matter without changing its chemical composition. For example, take here, suppose the matter is in solid state. If we heat this matter, it will become the liquid. This process is called melting. If we heat the liquid, it becomes the gas. This process is called vaporization. Some substances, they directly convert from solid state to the gaseous state. This is called sublimation. The opposite process is, suppose if we cool the liquid, it becomes the solid. This process is called freezing. If we cool a gas, it becomes a liquid. We call it as condensation. Some gases, they directly convert from gaseous state to the solid state. This process is called deposition. Okay, so one important point we have to remember, that is, during a phase change, whether solid to liquid or liquid to gas or solid to gas, during a phase change, the temperature remains constant. The heat supplied is used to break the intermolecular bonds, or we can say the heat removed is used to form the intermolecular bonds, not to change the temperature. So again, we have to remember this: during a phase change, the temperature remains constant. Okay, next, specific heat. What is specific heat? Specific heat means it is the amount of heat required to rise the temperature of 1 kilogram of a substance. Usually I remember, whenever specific comes, I remember 1 kilogram. This is my habit to remember. Specific heat means it is the amount of heat energy required to rise the temperature of 1 kilogram of a substance by 1 degree Celsius. We represent the specific heat with the letter C. C equal to Q over M into delta T, where Q is the heat energy, which is in joules, M is the mass in kilogram, and delta T is the change in the temperature. As it is a delta T, change in the temperature is the same in both in Kelvin scale and degree Celsius, so anything we can keep it. Okay, no issues. Either Kelvin, SI unit of the temperature is Kelvin, but here it's okay. So therefore the SI unit of the specific heat is joule over kg Kelvin, or we can go for joule over kg degree Celsius. Both are the same. Okay, so here, when to use the specific heat? Okay, in order to understand, let's focus here. Suppose here we have 1 kilogram of gold and 1 kilogram of aluminum. Suppose if we supply the same amount of heat energy to the 1 kilogram of gold and 1 kilogram of aluminum. The gold quickly rises its temperature, whereas the rise in the temperature in the aluminum is less. So it is very clear that different materials heat up at different rates. This is just because of its specific heat. The specific heat of the gold is different, the specific heat of aluminum is different. Its values are, suppose for the gold, specific heat is 129, whereas the specific heat of the aluminum is 900, nearly 7 times higher. Okay, so what is specific heat? It is the amount of heat energy required to rise the temperature of 1 kilogram of substance by 1 degree. Okay, only 1 kilogram of substance, 1 degree rise, whatever the heat energy required. That is the specific heat. The SI unit is joule per kg Kelvin, and the formula is C equal to Q over M into delta T. Okay, so when we use this specific heat, we use this specific heat when the substance is within a phase, either it is in the solid phase or liquid phase or in the gaseous state, not during the phase change. This is in a phase, then only use the specific heat concept. Okay, so here in this, if the heat energy is supplied, it is used to rise the temperature of the substance. That's it. Okay, for example, heat is given to a water which is at 20 degree, so that heat energy is used to rise the temperature within the same liquid state of the water. Okay, so when heat is added within a phase, the energy increases the kinetic energy of the molecules. This increase in the kinetic energy will increase in the kinetic energy is nothing but increase in the rise in the temperature. That's it. Okay, this is all because of the molecules moves faster. Okay, look at here. So it is very clear that different materials have different specific heats. Okay, for aluminum it is 900, we have seen for gold 129. So among this, the water, it is having the highest specific heat, so its value is 4186. Remember this number, this value may be useful for future. Okay, this is the specific heat of the water, joule per kg Kelvin or joule per kg degree Celsius. Okay, for water this much. And let's see for steam how much. For steam 2010, and for the ice 2090. Okay, so what is specific heat? It is the amount of heat energy given to a substance, 1 kilogram of substance, to rise its temperature by 1 degree. So how we calculate the specific heat? Using this formula. That's it. Let's do some problems on the specific heat. Okay, how much heat energy is required to rise the temperature of 100 gram of gold from 20 degree Celsius to 100 degree Celsius? Okay, so we have to focus only on the SI unit. So the mass, we need the SI unit. So 100 gram over 1000, which is equal to 0.1 kilogram. Okay, so that's it. So how much heat energy required? Heat energy, the formula is, okay, we know the formula, C equal to Q over M into delta T. This is the formula. So from this formula, the heat energy for Q equal to MC delta T. M is the mass in kilogram, that is 0.1. C is the specific heat of the gold is given, it is 129 joule per kg Kelvin. Nice. And the change in the temperature, that is delta T. Delta T is 100 final minus initial, 100 minus 20. Use the calculator. The answer is around 1 into 10 to the power of 3 joule. 0.1 times 129 times bracket start 100 minus 20. Yes, the answer is 1032 is the answer. Okay. I got this much answer, 1032 joule. Next problem. Lake Erie contains approximately this much of meter cube of water. So meter cube means it is volume is given. Okay, how much energy means how much heat energy is required to rise the temperature of this water from 11 to 12 degree. Only 1 degree rise means delta T is equal to 1 degree Celsius. Okay, so let's solve it. How much energy is required? So to do this problem, first we calculate the mass. Okay, mass of the water. So mass, the formula is mass equal to volume into density. All SI units we have to follow. That is volume is given 4 times 10 to the power of 11. The density of the water is 1000. Density of the water is 1000 in SI units, 1000 kilogram per meter cube. Kilogram per meter cube. So it means that the mass becomes 4 times 10 to the power of 14 kilogram. We have the mass of the water present in the lake. That's good. How much energy is required? So we know the formula Q equal to mc delta T. So m is 4 times 10 to the power of 14 times delta T. Delta T is only 1. Okay, C value, the specific heat of the water. Just now we discussed the specific heat of water is 4186. 4186. 4186 multiplied by 1. So use the calculator. Let's see. 4 times 10 to the power of 14 times 4186. That's it. The answer is nearly 1.6744 times 10 to the power of 18 joule. We finish. Next one. The next one is, if an electrical power plant releases 1000 mega means 10 to the power of 6 watt. Okay, mega means 10 power 6. Okay, 1 second. Okay, if an electric power plant releases 1000 megawatt means it's a power is given to us, okay, of exhaust energy continuously, how many years means time we have to calculate would be required to supply this amount of energy? Okay, so the B part, what is given to us? Okay, power is given to us 1000 mega. 1000 mega means 1000. Okay, let's write the power first. Power formula, power equal to energy by time. Okay, whatever it may be, 1000 megawatt. So it's nothing but 1000 mega means 10 power 6 watt. So altogether it becomes 1 time 10 to the power of 9 watt. This is the power is given. So from this we know the formula, power equal to energy by time. Energy by time. We have to calculate the time. Time equal to energy over time. Sorry, power. We can write like this. Okay, this is the energy, total energy required to rise the temperature of the water. So this much is the Q. This is the energy, that is 1.6744 times 10 to the power of 18 divided by the power, that is 1 time 10 to the power of 19. Okay, use the calculator. It's very clear. So 10 power 9 it becomes, so the answer is 1.6744 times 10 to the power of 9 second. So these many seconds it takes if we use the 1000 megawatt of the power to raise the temperature of the water by 1 degree. Okay, that's good, but he is asking the answer in the years. Asking the answer in the years. So very simple. What is the thing given? The hint is given 1 year equal to these many seconds. Okay, so 3.15 time, this is 10 power 7 second is equal to 1 year. How many seconds we got here? 1.6744 times 10 to the power of 9. 9 is more. Second means it will be more than 1 year. More than 1 year. So 1.6744 times 10 to the power of 9 over 3.15 times 10 to the power of 7 multiply with 1 year. So that's it. Use the calculator. 1.6744 times 10 to the power of 9 down 3.15 times 10 to the power of 7. The answer is 53.1. Nearly 53.15 years. Next problem. Water flows over a waterfall of height 110 meters. Okay, height is given, height equal to 110 meters. Okay, nice. Assuming that the entire loss of gravitational potential energy of the water is converted into the thermal energy. Gravitational potential energy, the formula the formula is mgh. This whole mgh is converted into thermal energy Q. So this is the thing we have to use formula. Okay, that's it. Calculate the expected increase in the temperature of the water. Okay, here we are neglecting the energy loss due to some other reasons. Okay, so we calculate the first Q equal to mgh. So m mass is not given. So we do one thing. Q equal to the formula we know is mc delta T. So mgh. M get cancelled. That's it. So but to calculate delta T we have to calculate. The formula is GH over the C. G value we will take 9.8. The height is given 110 meters. The specific heat of water 4186. times 110 over 4186. The answer is 0.2575 degree Celsius. Okay. Next one. Our next topic is latent heat. Latent heat. Okay. So far we have seen the specific heat. Here in the specific heat, whatever the heat energy supplied to a substance, then we found the rise in the temperature. Whatever the heat energy supplied to a substance, we found there is a rise in the temperature. Okay. The state of the substance remains the same. That is the specific heat. Now another topic, latent heat. Latent heat means here the amount of heat energy supplied to a substance to change the phase of 1 kilogram of a substance without changing in temperature. Here what is the change? The change is in the phase and there is no change in the temperature. Okay, so that is called the latent heat. Okay, we represent the latent heat with the letter L. Okay, L equal to Q over M. So therefore the SI unit is joule per kilogram. So that's it, we are ready. Again, latent heat means phase change. Phase change means it can be from solid to liquid phase change or liquid to gas phase change. Okay, anything it can be. So we will discuss what is the latent heat. Again, latent heat of fusion, latent heat of vaporization afterwards. So this is the general formula for the latent heat. So examples when we use during the phase change. Suppose if you take the melting of ice at 0 degree, the ice will melt here. Similarly, boiling of water, that is at water starts boiling at 100 degree Celsius. So then during this phase change we use the word concept of latent heat. Okay, so again, during a phase change the energy supplied is not used to increase the kinetic energy of the molecules. Instead, it is used to break the intermolecular bonds and overcome the binding forces so that the temperature remains constant. Okay, next. So a table is given where the latent heats of fusion and latent heat of vaporization for different substances are given here. Okay, so melting point, boiling points, all are given, complete table. Let's understand. First we start what is melting point. Melting point means it's a temperature where solid converts into the liquid at a fixed temperature. That is the melting point. For example, water at 0 degree Celsius, it will start melting and the ice becomes the water, solid becomes liquid. That is the melting point. Okay, for example, gold at melting point is 1063. Here at this temperature the solid will convert into liquid. Okay, so in this phase change process, whatever the heat energy required to change this solid to liquid, that we call it as the latent heat of fusion. Okay, so latent heat of fusion we represent with letter LF, latent heat of fusion, LF. So what is latent heat of fusion? It is the heat energy required to rise the temperature, or it is the amount of heat energy given to a solid material, okay, so that it converts into liquid at the melting point. Only at the melting point it will happen. Okay, so for the water, if this much of heat energy is given to the water, 3.33 times 10 to the power of 5 joule per kg. Okay, it means for 1 kilogram of water, 3.33 into 10 to the power of 5 heat energy is supplied. Then what happens? Okay, so 1 kilogram ice is there, it will convert it into the water. Okay, During this, the temperature remains constant, that is at 0 degree Celsius this will happen. The same thing we can observe here, that is from the liquid to gaseous conversion. Liquid to gaseous, suppose at 100 degree 2.26 times 10 to the power of 6. Okay, this much amount of heat energy is given to 1 kilogram of water. Okay, the water is at 100 degrees Celsius, that is the boiling point of the water. Then all the liquid will convert into the gas. Okay, so this is the latent heat of vaporization. We represent the latent heat of vaporization with LV, L suffix V. So just you remember the numbers here. Only for the water we remember, and rest we cannot. Okay, so we can use this table as the reference whenever problem comes on this topic. Okay, what is boiling point? Boiling point means a temperature at which the liquid will convert into the gas. That's it. What is latent heat of vaporization? It is the amount of heat energy given to 1 kilogram of the liquid for the phase change, to convert the liquid into the gas. Okay, let's do some problems on this. Okay, how much heat energy is required to melt 0.5 kilogram of aluminum? Mass is given in kilogram. Happy, that's nice. Aluminum material, okay, and its melting point, aluminum melting point is given 660 degrees Celsius. Very nice. How much heat energy is given? Just only melting. Only melting means it is related to phase change. Phase change comes, whenever phase change comes, we have to remember latent heat. Which latent heat? It is only melting, so fusion we have to remember. Okay, so only we need this information. Specific heat we don't require to solve this problem. Okay, how much heat energy means Q we have to find. Q equal to, the formula is M over, sorry, not over, ML. That's it. So M into LF. Mass is given 0.5. LF is 3.97 times 10 to the power of 5. So the answer is nearly 2 times 10 to the power of 5 joules. Okay, next problem. So here in this problem we find we have to use, this is the heating, so specific heat we have to use, and the melting phase change means latent heat we have to use. Okay, melting means latent heat of fusion. Okay, let's read the question. How much total heat energy is required? Q we have to find to rise the temperature of 0.4 kilogram of gold. The mass is given in kilogram. Very nice. From 25 degrees Celsius to its melting point, and then melt it completely. So for the gold information, in order to solve this problem, we need the gold information. That is, the specific heat of the gold is given. Very nice. And latent heat of fusion of gold is given. Very nice. Melting point is given. Okay, so the temperature is from 25 degrees Celsius to its melting point. Melting point is how much? 1064 degrees Celsius. So from here to here, two steps process. Two steps. Step 1 is 25 degrees Celsius to 1064. So melting point. Okay, this is step 1. Okay, so specific heat we have to use, and then it's melt completely. Melt means it's becoming solid to the liquid. So at constant temperature, that is at 1064, the solid will convert into the liquid. So here this concept latent heat we have to use. Okay, two steps process. So here the heat energy for this, the heat energy for this we have to find. So first case Q equal to, so there is a rise. So the first case specific heat comes MC delta T formula, which is equal to 0.4 times the specific heat of the gold is 129. The temperature is 1064 minus 25. The answer is 1039. So 0.4 times 129, the answer is 536.12.4 joule. Nice. This is the case 1, heating. Now the second step. So here we use Q equal to M into ml. That is 0.4 times 6.44 times 10 to the power of 4. The answer is 0.4 times 6.44 times 10 to the power of 4. The answer is 25760. Okay, this is joule. We want the total. So total means the heat energy for the step 1 and the heat energy for the step 2. We have to add 53612.4 plus 25760. So nearly the answer is 79372.4 joule. Okay, in the scientific mode we can write 7.9 1 2 3 4. Like this also we can write. This is the answer. Yes, we are coming to another important topic, that is the heating curve. Heating curve of the water. Heating curve of the water. Okay, so the heating curve of the water consists of total 5 steps are there. Okay, starts from the ice to the gas. Okay, the solid ice to the water vapor steam. Okay, total 5 steps are there. 1 2 3 4 5 steps. Okay, complete. So first phase is, so here whenever the water comes, we have to remember the melting point of the water, and another one, the boiling point of the water. Melting point of water is at that is 0 degree Celsius, boiling point is 100. Okay, so let's observe. Just take any number below 0 degree, that is minus 80 is given here. Okay, so the ice, it is the solid phase of the water. Okay, so till minus 180 till 0 degree, it is remains in the solid phase, complete solid phase. Whatever the heat energy supplied to this ice, it is used to increase the temperature of the ice. So it remains in the solid phase only whatever the heat energy is supplied, so it will use to increase the temperature. Okay, so whenever solid phase comes, please remember this formula, Q equal to mc delta T. So where C is the specific heat of the ice we have to take. Okay, specific heat of the ice is 2090 joule per kg Kelvin or joule per kg degree Celsius. After this, once the 0 degree, the melting point reaches, the ice takes some time. Okay, at this constant temperature, all the ice will convert it into the water. Okay, so all the ice converts. So here what happens, the phase change process has taken. Okay, in this, it starts here completely solid, it converts into completely liquid. So here in this, there is a mixture of solid and the liquid. So here phase change is happening, we have to use the concept of latent heat. Okay, so for the second one, we have to use this one. Okay, that is the melting of ice. There is a phase change at 0 degree. So the formula we have to use is m into Lf. So where Lf is the latent heat of fusion, that is 3.33 times 10 to the power of 5. Okay, suppose second step also finish, the third step. Okay, so here we have 100% of water we have. Okay, now here from here to here, whatever the heat energy is supplied to the water, so that is utilized in increasing the kinetic energy of the molecules, or you say in increasing the temperature of the water till the boiling point, till here. Okay, from here till here it remains in the liquid phase. So only whatever the heat energy is supplied, it will increase the temperature, that's it. So increase the temperature means specific heat. The concept of specific heat we have to use. The third one, Q equal to mc delta T, where C is the specific heat of the water. And then here once the boiling point touches, so here the water, it start becoming boiling. Okay, it takes much longer time compared to here. Here it will take much longer time. So at this constant temperature, all the water will convert it into the steam, the gas. Okay, so here start with 100% of the water. Now when it reaches here, all the water will convert into the vapor, gas, that's it. Okay, so this is phase change process. Phase change comes latent heat, so we have to remember the step 4. So the whatever the heat energy given in this process, it is only used for the heat phase change. So m into Lv. Lv means latent heat of vaporization, that is 22.6 times 10 to the power of 5 joule per kg. That's it. So step 4 is finished. Suppose here we have the steam. So if we heat the steam, so above 100 degree, it remains in the steam gaseous phase, only the temperature increases. If we heat this one above 100 degree, it will remain in the gaseous. There is no phase change, only temperature increase will be there. So step 5, so again specific heat Q, the whatever the heat energy is given, so it is used to rise the temperature. So the formula is mc delta T. So where C is the specific heat of the steam, that is 2010. So suppose we want to know the complete process. Okay, whatever the total heat energy is supplied, for example from the solid phase to the vapor state more than 100, so complete total energy if you want, you have to add Q1, Q2, Q3, Q4, Q5, that is the total energy. So heating curve of the water, it totally consists of how many steps? 5 steps, from the solid ice to the vapor, the steam. Okay, so let's, heating curve is nothing but it's a graph taking the temperature on the y-axis, the heat energy supplied to this is it is in the joule on the x-axis. So when we are going to the right means the heat energy is supplied, so temperature is supplied. So solid becomes liquid, liquid becomes the gas. Okay, next, for example, we are heating the ice from where? Minus 30 degree Celsius to minus 5. Minus 30 degree to minus 5. Minus 30 degree, sorry, here, from here. Minus 30 degree to minus 5. Only this much. Okay, so it remains in the solid phase. Once it is in the solid phase, only the whatever heat energy is given, mc delta T, same state will be there. So heat energy supplied is equal to mc delta T, where C is the specific heat of the ice we have to use, that is 2010. Okay, suppose we are heating the ice from where? Minus 20 to plus 20. So what happens? Minus 20 from here to plus 20 here. From here to here means how many steps? Okay, solid phase, phase change, and the liquid phase. Totally 3 phases are there. So the total heat energy supplied to convert the ice from minus 20 degree to plus 20 degree. So these 3 steps. So total energy means Q total equal to Q1 plus Q2 plus Q3. Next, some more example. Suppose we have the water at 20 degree and we have to take it to 120 degree. So what happens here? 20 degree to plus 120. So suppose we have, yes, here we have the water, we have to take it to here. So how many steps? 1, 2, 3. 3 steps. So step 3, step 4, step 5. Step 3, that is the heating of water, boiling of water, that is the phase change, and heating the steam. So the answer is the total energy if you want. So Q3 plus Q4 plus Q5. Okay, next. Yes, finished. Let's do some problems. Come on. How much energy is required to change 40 gram? Gram is not okay. Convert it to kilogram. So 40 divided by 1000, which is equal to 0.04 kilogram. That's it. From ice at minus 10 degree to 110. So minus 10 to 110 means total how many steps? Minus 10 to total 5 steps. All the steps are involved. Okay. So heating ice, what are the steps? The heating the ice, melting the ice, the phase change, then heating the water, then phase change of water, then heating the steam, all the 5 steps. Okay, all the 5 formulas. Slowly one by one we will use. What is the first step? Heating the ice. Heating the ice formula is Q1 equal to MC delta T. So the ice, which is equal to 0.04 times 2090 times from where to where? Only starting temperature minus 10 to 0. 0 is the final temperature. Minus of minus, it becomes the plus. So 10. So use the calculator. 0.04 times 2090 times 10. 836 joule. This is the which state? Heating of the ice. Heating of ice. This is the first step. Heating of ice. Finish. Next, Q2. Phase change. Okay, melting. So melting comes, Q means M into L into LF. So that is equal to M is 0.04, LF should be given. Okay, 3.33 times 10 to the power of 5. The answer is 0.04 times 3.33 times 10 to the power of 5. The answer is 13320 joules. Okay, this is what? This is the melting of ice. Melting of ice at 0 degree. This is happening. The story is happening at 0 degree. The finish. Next one, Q3. What is Q3? The heating of water. So water means MC delta T. The water value we have to take. That's it. So which is equal to 0.04 times for the water. 4186 time. Yes, from where to where? Water means till 100 only. Okay. So 100 is the final one. That is the initial one. The 0. That is simply 100 you take. So the answer is 0.04 times 4186 multiplied with 100. Okay, the answer is this is 16624 joules. What is this? This is the heating of water. Finish. Next step, Q4. Q4 means the water now it is at 100 degree. So 100 degree phase change will happen. That is the M into L into V. That is 0.04. L into V means 2.26 times 10 to the power of 6. 0.04 times 2.26 times 10 to the power of 6. The answer is 90400 joule. What is this? This is a phase change. Okay, so this is also a phase change. So what is this? This is boiling of water. Boiling of water at 100 degree. So this is a phase change. So finish. We are ready. The last step. What is the last step? That is the we are heating the gas, the steam. Okay, so whatever we do, it will increase the temperature. So MC delta T. So where C is the specific heat of the steam, that is 0.04 times specific heat of the steam 2010 multiply with final temperature we need. So now it is at 100 to 110, so only 10 degree. So 110 is the final temperature from 100. So altogether only 10 only. So 0.04 multiply with 2010 multiply with 10. The answer is 804 joule. This is heating of steam. Okay, in this complete process, the total heat energy used is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. We have to add all of them. 836 plus, okay, so let me write otherwise, 13320 plus 16624 plus 90400 plus 804 joules. 804 joules. Okay, 86 plus 13320 plus 16624 plus 90400 plus 804. The final answer is 121,984 joules. Okay, nearly we can say 122 kilo joules also we can say, otherwise keep this one as it is. Finish. Let's do the last problem. A 50 gram ice cube at 0 degree is heated until 45 gram has become a water at 100 degree, and the remaining 5 gram has become a steam at 100 degree. It is heated like this. Initially 50 gram ice is taken. It is heated until 45 gram become the water at 100 and 5 gram has become the steam at 100. Okay, so we can do this problem in different ways. So one method is, let's divide the 50 gram into two parts. Total 50 gram into two parts. So one is 45 gram, another one 5 gram. Let's solve this one separately. Think about 45 gram. 45 gram ice, it is heated until it becomes the water at 100. So let's focus here. We have taken the ice at 0. Okay, started from here. Ice at 0 degree. Okay, it is heated so that ice melts completely. Okay, at 0 degree. Then further it is heated until it becomes the water at 100. So this was happened. So here there is no phase change at constant temperature. So step 2 is involved. Now step 3, yes, whatever the heat is given, it is used to increase the temperature. So step 2 and step 3, this is for 45 gram. Step 2, melting of ice, and step 3, heating of water. Step 2 and step 3. Okay, step 2. Step 2 and step 3. Okay, that is M into LF, and this one is MC delta T. This is the specific heat of the water. So substitute the numbers. So 45 gram is 0.045 multiplied by LF. LF means 3.33 times 10 to the power of 5. Whereas here 0.045, the specific heat of the water, 4186 multiplied by 100. So find the answers. 0.045 multiplied 3.33 10 to the power of 5. The first one answer is, this one is 14985 joules. Here this one is 18837 joules. So in this case, for the 45 gram, so total value is, so add these two, this number and this number. Its value is 33,822 joule. Now let's focus on the second case, that is for the 5 gram. 5 gram, what happened? 5 gram started from the ice cube 0 degree to steam at 100. Started with ice, from here it started. Okay, phase change, then rise in the temperature of the water till 100, water at 100. Okay, then here, stop here. So this process total, step 2, step 3, step 4, step 2, step 3, step 4, melting of ice, heating of water, boiling of water. 2 3 4 2 3 4 2 3 4. Okay, so M into LF, here MC delta T, this is for water, and M into LV. That's it. So this is for 5 gram. So 5 gram means 5 divided by 1000. 5 divided by 1000, or you simply 5 times 10 to the power of minus 3 times LF. LF means 3.33 times 10 to the power of 5. So here 5 times 10 to the power of 3, specific heat of water 4186 multiplied by, this is 100. Then this one is M into 5 times 10 to the power of minus 3 times LV. LV means 2.25 26 times 10 to the power of 6. Let's find out. The first one is 1665 joule. The second one is 2093 joule. Third one is 11300 joule. So let's add all of them, the total value for 5 gram. So add this. The total is around 15058. Okay, now it's the time to add the total here. Okay, this plus this we have to add. So for the whole process, the grand total is 33822 plus 15058. The answer is 4880, which is nearly, you can say, 48.9 kilojoule. Thank you.